A cannon is fired from ground level at 30 degrees with a velocity of 30 meters per second. How long will the 9.25 kilogram cannonball be in the air? So what we want to figure out here, okay, is our change in time. Alright, so we want to know what our change in time is, how long it will be in the air. So we have a cannon, okay, little spark right there. Alright, and it shoots a cannonball, mind you, a 9.25 kilogram cannonball, and hits the ground on the other side. Okay, and this is 30 degrees. So, what we want to know, we do not really care for the 9.25 kilogram. This can be neglected because if you think about it, if we were calculating the force of the cannonball when it hits the ground, where we actually understand we actually need the weight or the mass of the cannonball. Sorry, not weight. Weight and mass are completely different. So with that being said, we have our velocity component, alright, and we have the velocities y component and the velocities x component, or x and y component, right? So our velocity in the x direction is going to be equal to, the cosine of 30 degrees times our velocity times 30 meters per second. And the velocity in the y direction is going to be equal to, go back to the pink color. Velocity in the y direction is going to be equal to the sine of 30 degrees times 30 meters per second. Okay. So, now that we have our velocity components, we know that in the x direction from a couple videos ago, I said that the x direction can be neglected to finding the value, since the x component, the acceleration is constant. We know that the velocity will remain constant as well. However, the velocity in the y component, we know that the acceleration in the y component is negative g. Remember? Alright. And since we know that it is negative g, okay, we know that we can integrate up with respect to time. So we will get the velocity, in the y component is equal to the sine of 30 degrees, this is our initial velocity of 30 degrees, minus g with respect to time. So we have our velocity in the y component, and this is actually sine of 30 degrees times 30. My apologies. We are multiplying sine of 30 times 30. So now we want to know how long the cannonball is in the air. Right? We want to solve for the change in time. We could solve for the change in time here. However, if we solve for the change in time here, since we integrate it up one level, we'll only get when the velocity is equal to 0. So we'll only get its maximum height. So we want to integrate it up again to the position function. We want to know at what time it starts at 0 all the way back till it hits 0 again. Because this, as you can see, is a parabola, an upside down parabola. And once we get the zeros of this, we can solve for change in time and we can get how long the object is in the air. So with that being said, I'm going to integrate the velocity function up again, and I'm going to get the position function. We're going to get the position function. This is actually, position function in the y direction is going to be equal to our initial position, 0, plus the sine of 30 degrees. Let's just solve this now. We know the sine of 30 is 1/2 times 30, so this is going to give us 15. Going to give us 15 meters per second. Since we integrated up with respect to time, remember, we need to multiply this by the change in time again. So we're going to get the change in time, keep forgetting to switch colors, minus our gravity divided by 2. Remember, we integrated up with delta t with respect to time again, so we are going to end up squaring this and dividing it by 2. So we get delta t squared, and then we divide all this by 2 because we integrated up. Alright, so now we want to know when this function equals 0 again. So we're going to set it equal to 0. So 0 is equal to 15 meters per second times our change in time, minus our gravity, 1/2 times 9.8, which is 4.9, times our change in time, squared. So now we want to solve for t here. Well, we could just plug this into the quadratic formula, and we'll get our value of t. So let's plug this into our quadratic formula. We know that our position in the y function is going to be equal to, opposite of b, okay, so we get negative 15 plus or minus the square root, of 15 squared, minus 4 times a and c. Now a is going to be 1/2 of our gravity, which is negative 4.9, times c, which is in fact times c. We don't have a c, so it's going to be 0. This will 0 out. Worked out nicely. And we're going to get negative 15 plus or minus, we actually have this all over 2a, which is negative 9.8. It's negative 9.8. Scroll down just a little bit. Okay. And we are going to get our position in the y direction. Is going to be equal to, negative 15. Remember, since we're solving for time, we are solving for change in time. Change in time is going to be equal to all this. Our change in time is going to need to be positive. So we're going to take the positive value of whatever we get here with the plus or minus. Well, the square root of 15 squared is just 15, so 15 all over negative 9.8. Okay, so we are going to get our change in time. Is going to be equal to negative 15 plus 15 over negative 9.8 will give us 0. Or we are going to get, let's say, bring up a calculator here. Going to get negative 15 minus 15 will give us a negative 30 over negative 9.8. So we're going to get a negative 30 over a 9.8 a negative 9.8. These positive out. We're going to get 30 divided by 9.8. And we get our change in time is 3.06 seconds. 3.06 seconds. Okay. Now this makes sense because our initial time was 0 seconds when we hit 0 first. So we started at 0. When we launched the trajectory, at 3.06 seconds later, we hit down here, which gives us our change in time, our final answer, equal to 3.06 seconds, which is how long we're in the air.